Hi, this is an introduction to logic. I'm Mark Thorsby, and this course overviews the basics of categorical, propositional, and predicate logic. In this video, we're looking at propositional logic, and we'll be discussing how to build indirect truth tables. So, welcome back, everyone, to indirect truth tables. Let me start off with the first thing, which is after I recorded our last video, which was how to build truth tables for arguments, I watched it and I realized that video is incredibly boring. Because if you go back and watch that video, I'm marking down that I'm building these truth tables, but if I have 16 lines, or I think I only did 8-line truth tables in the last video, you can see it takes a lot of time actually. And what I have for you here to look at here is I want to show you here. This is a little graph I put together where this, if just a sort of kind of brief review here. Let me put this on. Sort of brief review. Remember our equation here, L, the number of lines for a truth table equals 2 to the nth power, where n equals the number of unique variables. So what I have here is each of these are unique variables. And what I've done is I've done the equation for you. You can see that when we get to 10 unique variables, we need well over 1,000 lines in our truth table, right? And now think about it for a moment. When we make ordinary language arguments, for instance, I don't know, last night when I recorded this was a presidential debate. When you watch these presidential debates, think about how many propositions the political candidates are actually putting together to make their arguments, right? In terms of variable size, it's probably well over 10. You can see when we get to 10, the capacity to actually analyze an argument using truth tables becomes basically just impossible. You would literally need an Excel spreadsheet or something. You definitely would need a computer program to actually analyze what people are doing in ordinary language. Now, that's sort of interesting because one of the things it means is that it represents the tremendous capacity of the mind to actually, when we have an ordinary language conversation with anyone, when we're just conversing and making arguments, that our minds are actually fabulously rich in terms of their capacity to analyze multiple things at once. On the other hand, you can see with as more propositions come, that means there's greater and greater likelihood, frankly, that an argument will be invalid. Okay, which is why some people have been, I think, incorrectly led to think that when we do deductive arguments, we begin with the smaller points and move forward in terms of our knowledge. So, and you can see why that's the case is because if you start with a lot of variables, there's a high degree of likelihood, most likely, that it's going to be invalid, right? But that's just an astronomical number. But it also means that what we're doing in logic here is only really scratching the surface of what our minds are already capable of. So, and you watched that last video, and it was difficult to watch because it was so long because it took me a while to build this. So what are we going to do today? Today we're going to introduce the short method, the quick method for actually analyzing arguments. We're still utilizing the basic mechanics of truth tables, but we're going to see by using the indirect method, we'll be able to, in a much shorter time, be able to assess arguments that have many, many variables at once, actually. So, and there are places in which this is a bit tricky. So, what are the basic steps? Well, it goes back to our concept of validity, right? And I know for many of you, this is sort of kind of me, like a broken record here. But what is a valid argument? A valid argument is an argument where all of the premises are true, right? And the conclusion is false. That's what invalidity. That's what an invalid argument is, right? So that means that what we've been doing in truth tables is we've been building these truth tables and then looking for specific lines in which all the premises are true, but the conclusion is false. If we can find one line like that, that proves the argument invalid. So for instance, let me do a quick problem here. I don't want to spend too much time on it. But let's say we did this example. Not A If not A, then B or C, right? You have not B, therefore C, if C, then A, right? So here's the arguments, right? If Andrew doesn't go to the party, then either Bob's going or Charlie's going. Bob's not going, therefore, if Charlie goes, Andrew's going to go, right? That's the argument. It's interesting, once you put it into sort of ordinary like language, you can sort of assess, that doesn't sound like too strong of an argument, but let's see how it works, right? So if I have to build a truth table here, you can see I already have 3 lines. It's going to take me a while to do this. So let's do something in reverse. This is called the indirect truth table method. We might even just say it's the reverse truth table method. Indirect truth table method. And what we're going to do here, what are our steps? Let's see if we can write these over on the side here. The first thing we're going to do is we're going to assume that the argument is invalid. So the first thing here is assume invalidity. And we're going to then we're going to enter our assumption into the truth table. Enter the assumption. Enter the assumption. So what would the assumption look like if this was a truth table? Under all of the main operators for the premises would be true. And under the main operator of the conclusion, it would be false. So let's just enter that in now, right? And that would be, this would be true, and this would be true, okay? Since these are the main operators, you can see this would be an example in which this is invalid. So what we're going to do here is by entering our thing, we're going to then go backwards. We're going to sort of work our way backwards. And what we're going to try to do is see if it works out. If our assumption doesn't break any of the logical definition rules we've been looking at in this, that we've been using for propositional logic, then this will turn out to be a case in which it's false. So we enter our assumption. And after an assumption, what we're going to do is we're going to work your way backward. Looking to see if you break any rules. And you're going to get a sense of what I mean by this in just a minute. Okay, so let's do this now. So how do we do this? Well, if I'm going to it's oftentimes, and I'm going to always recommend a sort of hint, is always start with the conclusion. It doesn't always work in that. It doesn't always work best to start with the conclusion, but typically it does. So let's start with the conclusion here. Remember, if we go back to our definitions here, and I wonder if I can pull them up in the textbook here, because I think it's helpful for you guys to see those. Let's see. I think I've got. My apologies here. Oh, never mind. There's an insert that if you buy the textbook, there's an insert, or if you have the textbook, for instance, you'll notice if you go to in between the back cover. Where is the rules? I'm sorry here. I should have had this prepared. Oh, they don't have them. Okay, never mind. I'll just have to edit this out. Let's go back here. Let's go back here. So let's just work our way through this problem. Okay, so there's only, if you go back to the definition for a conditional, the only way that this can be false is if this is true and this is false, right? Only if this is true and this is false. Now, what do I mean by work your way backward? Once I know the values of one, I can enter those same values in the rest of the line, because remember, they'll all be consistent. So enter your values consistently across the equation. Or across actually the argument. So that means that if A was false here, anywhere there's an A, it needs to be false. Okay, anywhere there's a C, the C needs to be true. Okay, now let's work our way backwards. Now you can see here So okay, the conclusion I've entered in, my assumption's working out so far. Now let's move here to this premise here. If this is true, then B has to be false. So now let's enter in B is false. Okay, so now my assumption for invalidity is still working, right? Because when I'm looking to see if I break any rules, because if I break a rule, that means that I've actually committed a contradiction. So let's see here. Now let's start with A. If A is false, the negation of it's true, right? Okay, so if the negation of this line is true, and maybe here we can put a little, right? So here is the main operator. If the negation of this is true, then in order to maintain my assumption here, because this depends upon this being true. If this is false, then it fails. So let's go back to our assumption. Let's just see if we break any rules. If B or C, it would seem that in order, because if this was false, then we would break the rules. But this is actually true because in the disjunction rule, all you need is one of them to be true in order for the whole thing to be true. And since the C is true, that means this is true. If this is true, a true and a true using the conditional rule is true, which means that this also works out. This is an invalid argument. Because you can see what I've done is, instead of looking for, because this I would have to create 8 lines, instead of creating all 8 lines, I said, let's just start from the back and start with all the possibilities for it to be false and work our way backwards and see if we can discover an instance in which we commit a contradiction, because we did commit a contradiction here. I think the best way to do this is, let me do another example here and you can see how to do these problems over and over. So let's try another one here. Sorry, I feel like my explanation skills are sort of waning. Okay, so here's another problem. If A, then B or C. B, therefore D. A, therefore not C. If not C, then D. Oops, that's a D. Let's erase that. Okay, so let's do this problem here. Now, let me go back here and actually finish the steps. Oops. So what are the last steps here? Number 4 is enter your values consistently. Number 4, if a contradiction is discovered, the argument is valid. If not, that's an R. It's invalid. Okay, so this is an argument. So going back to our example here, we made the assumption of invalidity. We did not commit a contradiction, meaning we didn't break any of our rules. Therefore, this argument is invalid. So let's do this problem here. Okay, let's start off by making our assumption. That's the first thing we do under the main operator. So that's going to be false. And then this is going to be true, true, true. Okay. So the only way for a conditional to be false is if this is true and this is false. Now, if the negation is true, that means the C is false. So now I have all the values for C, D, and A actually. So let's enter them now. So this is this is going to be an F. Let's see, all of the D's. All of the C's are F's. Okay, and all of the A's are true. Okay, so let's take a look at this. Let's start with this. Now, okay, so in order for this conditional to be true, because you can see this one checks out, our assumption's working. What about in this premise here? If B, then D. The only way for this to be true if D is false, because remember, if this was true, right, if B was true, then that would break our rule, because then it would be true, be false. So B must be a false value. So B must be false, okay? Now I'm going to move over here. I now know the value of B. B is false. Now, what's the rule for disjunction? In this parentheses here, is that at least one of them has to be true in order for it to be true. So this is false. But wait a second. Now I'm comparing a false and a true statement using the conditional rule. But that is actually false. But my assumption was that it was true. You can see here that that means that this conditional needs to be both true and false at the same time for my assumption to work. Do you see that? Because it needs to be true for my assumption, but of course my assumption required me to also say it's false. They can't both be the same, which means that this is a contradiction. Because I've discovered a contradiction, then that means my assumption is false, or my assumption fails, and the argument is valid. Okay, so you can see here what I would do is I would just circle this and write valid, right? Because this is where obviously you commit the contradiction, right? So again, the steps: assume invalidity, enter the assumption, work your way backwards, looking to see if you break any rules, enter all your values consistently, and then number 4, if a contradiction is discovered, then the argument's valid. If not, it's invalid. So let's do another problem here, because I want to do 2 more problems here just so you get a sense of it, but I hope you can see that this is much, much faster than doing it the way we've been doing it in terms of building truth tables, right? So what if we have if A, then B, if C, then B, therefore, if A, then C. Now, by the way, if we put this into argument form, it'd be like, if Andrew eats birthday cake, then Bob will eat birthday cake. If Charlie eats birthday cake, then Bob will eat birthday cake. Thus, if Andrew eats birthday cake, then Charlie's going to eat it. Okay? So the question is, does that make any sense? So let's begin our assumption here. And if you want, pause this video, because I'm just going to do this real fast. Pause this video, and then see if you get the same answer that I do. Right? So this is going to be true, false, A is true, C is false. So if this is false, well, now it's interesting here. So you can see here, if this is false, then B could be true or false. So my goal is ultimately to make sure that I test all the possibilities for invalidity here. So let's enter both values now. So let's say we have, if this could either be false in order to make this true, or this could be true, and it would also maintain the consistency. You can see here, whenever you recognize through the rule that there's multiple ways in which this could be true, you have to list them out and build truth tables for all of them. And that's one of the difficulties of using the indirect truth table method, is that you have to work through all possible contingencies to make sure that your assumption for invalidity doesn't work. Because it may not work on one line, but it may work on another line. So this is an inherent difficulty, because if we had this would mean that if we had 1,000 unique variables, it would also be very difficult to solve the problem for the same reason, because you have less things to run through than a truth table, but still it'd be quite a few. So that means that B can be false or true for our assumption to work. So let's go look over here. In order for A, if A then B to be true, right? If this is true, B has to be what? B has to be true. Right? You can see if I put false here, it would look like I committed a contradiction, right? So that's not the case. But let's go back down here. So this line looks like it commits a contradiction, right? You can see right there, because true to false can't be true. But if I assume that it's true, because this was a possibility, then that and A is true, then that means this would be true. So that means that I found this is the assumption works. Now, and because it works, it's invalid. Because I assumed it was an invalid argument, and now I've proven it. Right? Now, but see, the reason this is a good example here is because you can see that if you just did this first line and then went on your merry way, you'd think it's a valid argument when it's not actually a valid argument. It is possible for the premises to be true and to have a false conclusion simultaneously. Okay, now let me quickly talk about one more thing before I do any more problems. Is we can also use the indirect truth table to test for consistency of statements. And here, just to give you an example, let's imagine that we have, that we are detectives, right? And that we're detectives and we're trying to solve a murder case, right? So the example here is, think about detectives. We're trying to solve a murder case. And we have three different witnesses, right? We have three different witnesses. We have witness A, and we have witness B, and we have witness C. And each of these witnesses has given us specific statements about what they saw in terms of the murder, right? Let's say that the witness A here, the first witness, says, I don't know what their proposition is, but it can be symbolized as C, if C then B, right? And let's imagine our second witness here says, no, it was not B or C. And then our third witness here says, it was C if and only if B, right? Let's imagine that each of our witnesses gives us these three statements. As a detective, we would want to know whether or not these statements are consistent, right? We want to know whether or not they're consistent, because if they're consistent, then that means everything they're saying checks out, or at least that, it's all in sync, if you will. If their statements are inconsistent, right, that would mean that someone is lying, right? Someone is lying, it would seem. So, especially if two of them are consistent, but the other one's not. So what we're going to see here is that we can use, you can notice here there's no conclusion. These problems there's no conclusion, so these are not arguments. We're just trying to test whether or not arguments can be consistent. And here's what we're going to do is we can use the truth table method in the same way, right? But then if a contradiction is discovered, pardon me. If contradictions mean inconsistency, and then no contradiction means that the arguments are consistent. Okay, so contradiction means inconsistency, and if there is no contradiction discovered, it means the statements are consistent. So let's test for them now. So what we do is we assume that they're all true. Put enter T for the main operator. And then let's work our way backward and see if we can discover a contradiction or not. Now let's start, I always say start with the conclusion, but you can really start anywhere on these problems as long as you're consistent in terms of your approach and you test all possibilities. So you can see here, what are the ways in which C if and only if B could be true? Well, there's two ways it could be true. If C is true and B is true, it's true. But also, if C is false and B is false. That would be another example in which the conclusion could be true here. So you can see C or B can be true or false. So let's run through this first line and see if we can find a contradiction. So that would mean that C is true, right? And B is true. If B is true, then that means the negation is false, right? If B, you can see here you have a false or true, right? That doesn't break the rule for disjunction, because disjunction is that you just have to have one of them be true. In this case, the C is true. So our assumption here seems to be working. So let's enter in our values. Our B value is true, and our C value is true. True, if C then B, if true to therefore true, that's true. So that means it works out. Our assumption works out here. But we still need to check this second line. Because remember, if we find a contradiction, we'll know that that these statements could be inconsistent. And since we're detectives, we want to do a good job with this. So this is going to be false. B. What if B is false? How do things work out? And what if C is false? Right? Okay. So if B was false, the negation of B would be true. And so you have a true, using the disjunction rule here. True to false is still true, right? I'm sorry, true or false is still true. And so that means, okay, that means it seems to be working out here. Oh, that's problematic for us. So if we said C was false, let's take a look at it here. If C is false, right? If C then B, the rule for the conditional is that that would be true. Okay, so now we've checked all possibilities. right? In which that could be the case. Um, yeah, so that seems to be, I think, I'm trying to make sure that we were totally consistent here. Is there any other possibilities? If this is true and this is false, what happens if this was true? No, because yeah, this is done. I'm sorry. I'm not doing good on this video, but that's all right. So this proves that there's no contradiction, so that means these statements are consistent. These are consistent statements. The reason I was sort of sitting there trying to double check, what I was double checking, is whether or not I had to move the disjunction. But you can see here, the biconditional requires this. So it determines that these are the lines that these have to be. But both of them are subject worked out, so that means this was in a consistent argument. Okay, let's go here. I want to show you one last thing here from the textbook. Okay. So in terms of indirect truth tables, this is what the chapter looks like. But I want to draw your attention to a specific passage that Patrick Hurley includes that's worth reading. Here's the 3 final points need to be made about indirect truth table arguments. First, if a contradiction is obtained in the assignment of truth values, every step leading to it must be logically implied by some prior step. In other words, the contradiction must be unavoidable. If a contradiction is obtained after truth values are assigned haphazardly or by guessing, then nothing's been proved. The objective is not to produce a contradiction, but to avoid one if possible. Okay? You can see here, it's a great little thing. If you assume the argument's invalid and there's a contradiction, it's valid. If it's not a contradiction, it's assumed invalid. Okay? And the same thing here goes in terms of consistency, right? If your contradiction is discovered, it's inconsistent. If there's no contradiction, then the argument's consistent. You can see here's a number of different examples. It's not very difficult to do. Let me just do 2 problems here from the homework set, just so you can get a sense of how we're going to do them. Let's do number 17 here. Let's do 17. Wait, hold on a second. I better check the instructions here. The instructions here is, when possible, compute truth values of the simple components of the following compound propositions. If no truth value can be computed, write a question mark. So let's take a look at number 17 here. It's not a full truth table problem, but let's just take a look at it anyway. So here's what we got. Okay, so if this is true, if we want to maintain the truth functionality of this statement, right? If this is going to be true and this is true, then the negation, notice we're starting with the negation, not with the P. The negation cannot be false, because if it was false, remember we said that, right, we said if A to B, in order for this to be true, it's true, true, false, false. That's going to be true, false, true, false, right? This is true, false, true, true. Here's the definition here, right? So since this is true and we want to maintain our assumption of truth here, then that means these are the 2 possibilities we're going to look at in terms of the definition, right? And now you can see that if it turns out to be false, then that would make our main operator false. We don't want that. We want to keep our truth condition. So that means that this thing has to be true under the negation. So that's got to be a T right there. If that's a T, then P is false, right? Do you see how we did that? We're just using the definitions in order to figure it out. That's a fairly easy problem to do. Let's take a look at the section 2. Use the indirect truth table method to determine whether the following arguments are valid or invalid. I'm going to scroll down and do one here that's maybe a little longer, so you can see how to do it. One of the things you'll find in terms of doing these problems is that when you use I'll do number 6. One of the things you'll find that when you do these problems is that the conditionals, you always like the conditionals because there's only one way for the conditionals to be true. The same thing goes with the conjunctions. There's only one way for those to be true. The ones that are tricky is when you have the disjunctions. Because the disjunctions mean you can do multiple things. That's why when I see a problem, what I generally try to do is do my disjunctions and my biconditionals last. I don't rush into doing those because I want to let the conditionals do the work for me, if that makes sense. If you have no idea, if you're confused by what I'm talking about, if you just start doing these problems over and over, and sort of, you'll see exactly what I'm talking about naturally. It's kind of like when you learn to play poker. At first, you have no idea what you're doing. I still don't, but I always lose my money. But after a while, you sort of get a sense of the game. It's the same way, and that's, by the way, what I would recommend is you'll do really well in these problems and logic here on out if you can really just sort of see what we're doing here as a game. And the goal, and what we're doing is we're just changing the rules with each session, with each video. And then what we're going to do, and then you'll enjoy it, ultimately. I think that's the trick, is to learn to sort of enjoy what you're doing in logic. But we'll see how if we can do that. To see it as a game, as sort of a puzzle, is how you'll ultimately enjoy it the best. So I'm going to always start with the conditionals. You can see I want to end over here with the disjunction, because the disjunction, there's 3 different ways. So if I start here, I've got to lay out 3 different possible lines. I don't want to do that. That takes more time. The whole point of the indirect truth value is do it quick. So if this is false, then this has to be true and this has to be false, right? Because which would make E true. So now that I know A, now that I know the A values, let's put them in true. And now let's put in the E value, which is true. Okay, now B, so that one's done. Let's look here at this one. If this is true, the B has to be false. So let's input that, false. Okay, now let's jump over here. You can see this is where it starts to suddenly get a little tricky. Which one should I do first? I have more I have the same amount of, no, I have more values inputted here. So let's stick with this one actually. Let's hold off on doing this third one. You could start here. It's just going to take you a little bit more time to do it, but we're going to see why we're going to do this. Because in order for, since I know that A is true and I have a conditional, the only way that this could be true is if this is also true, right? So in order for this to be true, right, because B or C, if they're both false, it turns out to be false, which means that it needs to be true. So C's value is true. That helps me tremendously now, because now I can take a look at this one. If C is true, right, and I want to maintain my condition, then that means the conjunction cannot be false. It must be true, right? What must be the case in order to mean this would be true? If you have D and E, the only way that compound conjunction can be true is if both values are true, which means this must be true. So you can see here, what I've discovered is that this argument is invalid, because my assumption works out. I never discovered a contradiction. It also means simultaneously that my parentheses are consistent. So you might say that this argument is an invalid argument, but that my original assumptions, my premises here, were actually logically consistent, right? Even though it's invalid. Okay. Number 3, it's also done. Okay. So that's our video for indirect truth tables. In our next video, we'll be moving on to natural deduction, and we'll be talking about how to actually make positive proofs instead of trying to prove invalidity. In our next series of videos, we're going to try to prove we're going to look and see how to prove that something is valid in a positive sense. Okay, that's enough for me. I'll see you guys online.